In this video, we are going to review other historical number systems and introduce the idea of a positional system. Earlier, when we learned about the Egyptian numeration system, we saw that if we wanted to express 2,000, we had to write the symbol for 1,000 twice. If we were trying to write numbers that were much larger or more complicated, though, a system in which you have to repeat the characters as many times as you want to have them express could become very bulky and difficult to work with. This is one reason why positional enumeration is helpful. In positional enumeration systems, the location of the symbol has an implied meaning, and we're going to look through that first by how our number system has an implied meaning based on where the number is written. I'd like us to look at the number 16 and 61. Whenever we look at the number 16, we have just memorized that this is the number 16, but if we were to break this down based on our number system, we would first say, well, this is what we call the tens place, which means we have 1 times 10, plus this is what we would consider the ones place, which would mean we have 6 times the number 1. Altogether, that gives us the value 16. Now, our number system is a base 10, so every other position we have to the left of the numbers increases by tens. So this would be the hundreds place, the thousands. Next we would see the 10,000s, 100,000s, millions, 10 millions, 100 millions, and billions. Each of these, for every position to the left that we go in the number, we increase our multiplier by 10. Now, the reason we see 16 as visually different than 61, notice they're made up of the same characters, but the location gives a different implied meaning. Now, since the 6 is in the tens place, this means we have 6 times 10, plus now the 1 is in the ones place. 1 times 1 would give us the value of 61. Our number system is a positional number system of base 10. Let's next look at the Babylonian system, which was a positional number system, and it used a base 60. Now, the Babylonian system had two symbols. The symbol for 1 was this inverted triangle, and 10 was this symbol like this, and it seemed to have a little bit more shading towards the end, but if you like, just feel free to write it like that, just some wedge. You don't have to worry about the shading on the interior so much. With these two symbols, along with a base 60 positional system, they could express any digit. Now, the Babylonian system wrote like we do the smallest base, and then to the left, okay? So the first groupings of symbols was what we would call the base 1. Just like in our example of 16, the 6 was in the ones position. And then all of these little brackets weren't actually written in the numbers. I'm just drawing them to help us visualize the base. The next set of symbols, if it was there, represented that many symbols multiplied by base 60. And if we were looking at very large numbers, then we would also include a third set of symbols, and this symbols was going to be multiplied by the base 3,600. And the way these are in common is actually 3,600 is equal to 60 squared. So this was 60 squared, this is 60 to the first power, and anything to the 0 as an exponent is 1, so 1 is the same as 60 to the 0th power. So this is why we say it's base 60. The first entry has 60 to the 0, which is 1 base. The second entry has 60 to the first, which is just 60 as the base. And the third entry, if it's there, has 3,600, which is 60 squared as the base. So keep in mind, our system is base 10, but this Babylonian is base 60. If we wrote the number, suppose we were going to translate this symbol. We see that it is Babylonian because it is made up of the two symbols that are represented in the Babylonian system, but how would we translate this? For instance, we don't have the brackets written like we were described here to show the base. The way that you know how to, whenever you're looking at one base to the next in the Babylonian system, is it always writes larger digit first to the left and then smaller digit coming after it. And if that order is ever switched, that means you're looking at a different base. So starting here, we've got our ones digits here, followed by a group of 3 tens digits. But then do we see that after the tens digit, we revert back to a 1 digit here? That means we've started a new base. So if you ever see that you've got ones and then tens, but then it becomes a ones again, that means this is a different grouping. So this is implied to have 2 groupings. The first would be our base 1. The second would be the base 60. And in this case, since there's no third grouping, since it doesn't change again, we would not have a base 3600. Now we need to translate this. This represents 10, 20, 30, 31, 32, 33. So we have the symbols for 33, and since it's in the first position, that would be a base 1, so we multiply that by 1. Then we add it to the remaining numerals, so this is 10, 20, 21. Since it's in the second position, we multiply it by base 60. 21 times 60. Now we get our calculator and we type 21 times 60 plus 33 times 1 to get what this number represents in our number system. And this number would represent 1,293. Let's look through some other examples involving the Babylonian system. A few features. First, we've got the base system described like we talked about previously. It's a base 60. The smallest base is always to the right, and then as we move to the left, we increase the base by multiplying by 60. We're not going to see any problems with a base higher than 3,600. Now, the earliest Babylonian system historically lacked the 0 symbol. So in this case, if we wanted to go from base 1, but there was not a base 60, we just wouldn't write the base 60 and we would go to base 3,600. But that could be somewhat confusing because do you just skip a certain amount of distance? And if scribes were reading it later, it would be unclear whether you wrote a base 1 and a base 60, or a base 1, skipped the base 60 and went to base 3,600. So for our class, if we ever have that one of the bases is missing, I will have it written something like this. This would be an example of a Babylonian symbol where the base 60 is missing because there's just nothing written here. Okay. Now I have added in these brackets to make it clear that this is the first section of the base, which is base 1. And we've got 11 times base 1 plus 0 times base 60 plus 30 times base 3,600. Okay. So if you ever see it written where there's just an empty bracket, you're implied that there is 0 in that base. But that is one of the issues that our current system has improved upon. We've got the 0, which allows us to have a 0 in a certain base. We've got 2 examples that we're asked to convert to Hindu Arabic form. Remember, Hindu Arabic form is just our number system. Starting at the right and then moving towards the left, I'm going to look. Here I've got a group of 1s, and I'm going to just glance. Do I ever have groups of 1s again? No, it just goes from 1s to 10s. Since there's no change, we're going to assume that this is all one base. We've only got one section, so all of this represents base 1. So this would be 10, 20, 30, 40, 41, 42, 43. So this is going to be 43 times the base 1, which would just be 43, is how this would translate. Now as we look at our next example, B, we see we've got a grouping of 1s and 10s, but then do we see it switches to 1s again? That indicates that you're actually in a new base, so this would be the first grouping. Okay, now we have these 1s, and we see it becomes 10s again. This would be implied to be the second grouping. So the way you know where the groupings change is if you ever have 10s, and then to the left of them you see 1s again, that means they're in separate groups. If it helps us, we're going to remember that, okay, the first group is base 1. The second group represents base 60. Because as you go to the left, the base increases by a multiple of 60. Recalling the symbols here, for the base 1, we've got 10, plus another 10 is 20. 1, 2, 3 for the symbols of 1. So this would translate to 23 times base 1. So remember, the first position is implied to be this number, whatever it represents, times 1. The things in the second position is going to be whatever this number represents times 60, and we'll add those together to get our final answer. So we have 10, 20, 30, 40, 50, because this is the symbol for 10, so that's 50. And then 1, 2, 3, 4, 5, 6. So this is 56. Since it's in the second position, it's implied to be multiplied by 60. We will find this value carefully in our calculator and write our final answer here. And we would get 3,383. For this next problem, I recommend that you pause the video at this point and work on it on your own in your paper. Remember that you're going to be looking, do we ever switch from going from 1s and 10s? Once you get a 10s position to the left, does it ever switch back to a 1? If so, that's how you're going to find your groupings of the bases. And then remembering that we've got a base 60 system, the first base to the right is base 1, the next base to the left of that is base 60, and continuing on to 3,600. Work on this problem and unpause whenever you're ready to check your work. So I'm going to always start at the right and then go to the left. I see I've got a groupings of 1s followed by 10s, but then I see after this grouping of 10s here, we actually have another 1. That means everything before the 1 was in its own group, so that's our first group. Now I've got a 1, it switches to a 10 again, but then after 10s, it switches to 1s again. That indicates everything before this one and after the first group is in its own group. Okay. Then we double check. It is 1s and then 10s and nothing else. So here we've got 3 different positional groupings. Always the group to the farthest right is the base 1, then base 60, and then base 3,600. I definitely recommend going through all this scratch work off to the side. It's going to help improve the accuracy of these problems. So now we go base at a time. The first position has the number 10, 20, 30, 31, 32, 33, 34. Since it's in the first position, we're going to multiply that by the value 1. Plus here we've got 10, 20, 21. Since it's in the second position of the Babylonian system, it's going to be multiplied by 60. Plus 10, 20, 21, 22, 23, 24, 25. That'll be 25, since it's in the third position, times 3,600, which is 60 squared. Okay. Carefully evaluating this in our calculator, we'll get this numeral as represented in our number system, and we would get 91,294. Now, all of these examples have been taking Babylonian symbols and then translating them into our numerals. We're soon going to see the opposite example where we go from our number system to the Babylonian number system. We're going to begin by writing 733 in the Babylonian form. Whenever you're going from our numbers to their numbers, I recommend just tracing out the basic bases that we've got. We've got 3 different bases. I'm drawing these brackets just to help me organize and think of it, where the first section shows the base 1, second section shows base 60, okay. Third shows base 3,600. And then the way you would know what is the highest base is you would ask yourself which of these, 1, 60, 3,600, while there are other bases, we're not going to deal with anything higher than this, can be divided into the number that we're looking at. So definitely 733 can be divided by 1, 733 could be divided by 60, but 733 could not be divided by 3,600 because that's too large, it surpasses it. So the highest base that can divide our number is base 60. So off to the side, we would first in our calculator figure out, okay, 60 divides 733. And here we're going to look for the exact number. So type this into your calculator, and it divides 12.2166, repeating. Now what's going on here is we don't really care about the decimal. All we want to know is that 60 goes into 733 12 equal times. And if you wanted to check in your calculator, 60 times 12 would give us exactly 720. So for the base 60, we would want to represent that 12 goes with the base 60. So we're going to eventually write this in the correct symbols, but 12 goes there. Now, if we have 12 base 60s that we're going to subtract from our original number, that would get us to 720. That means there's only 13 remaining digits that we have to take care of. We always go from the highest base to the smallest. Now we see after we've taken care of base 60, we've got 13 remaining digits for base 1, but definitely they could just be written with 13 ones here. So we need to represent 13 in the base 1 in Babylonian symbols, 12 in the base 60 position. Okay. To represent 13, you would have a 10, and then 3 of the ones. And if you want, you can stack the ones if you don't want to always write left to right if you're running out of space. So long as we've got the position of ones come before tens, right to left, that's correct. That would be our base 60, or base 1, excuse me. For base 60, we have to write 12. So we would write a 10 and 2 ones. Okay. And if you like to draw these brackets just to help you visualize the different bases, you can, or you could just write it just as this would be our answer. So just as a wrap up, how you go from our number system to Babylonian, you first think of the Babylonian bases 1, 60, 3,600. What's the largest base that could evenly divide into the number that we're given? You find how many times that divides. We found in our case it was 12 perfectly. You find how close that would get you to the number you're trying to represent. In our case, we got to 720 when we were wanting to represent 733. So then you just have to account for the remaining distance with the lower bases. Let's go through another example together, and then I'll ask y'all to work on one on your own when you pause the video. Here, if we're looking at 7,904, now we need to consider with base 1, 60, and 3,600, what's the largest base that could divide it? And definitely 3,600 would divide 75,904. In your calculator, do 75,904 divided by 3,600. And when we're doing this, we're looking for how many times would 3,600 evenly divide this digit. And we would get 21.08 something. Remember, the decimal place isn't as important here. We just care that it divides 21 times perfectly. Off to the side, we would see exactly what is 3,600 times 21. How close does that get us to the value we're trying to find? Okay. And we would get to 75,600. Now we want to represent 75,904. So eventually we're going to write 21 in the base 3,600 position in Babylonian symbols. But that only gets us to 75,600. We need to figure out how much is remaining to be accounted for. So this is all work done off to the side. You would take the original number, subtract out what we've accounted for with this base. Okay. And we need to account for 304 remaining. And definitely feel free to do this in your calculator just to make sure there's no error. Now we have to ask ourselves, how can 304 be represented by base 60? So off to the side, you would take the amount remaining, 304. The next base that we're trying to represent that by is base 60. We're going to be decreasing through the bases. So we would divide that by 60. And it would be something like 5.06 repeating. Again, we don't really care about the decimal. We care that 60 goes into 304 exactly 5 times. Let's see how close that would get us to the 304 that we're trying to represent here. 60 times 5 is 300. So we ask ourselves, how close are we to the digit we're trying to represent? We are only 4 away, but our last base is the base 1, so if we just have a 4 here, that would account our number. Now, really quick, before we write this in symbols, let's double check. In your calculator, find 21 times 3,600. That's what 21 in this position would represent. Plus 5 times base 60, plus 4 times base 1, and we know that we found the correct representation if all together this equals the number we started with. Take a moment to calculate that. And indeed, we would get 75,904. Now we do need to translate this into Babylonian symbols, so we've got 21 needs to go in the third position here. So that would be 2 10s and a 1. That's our 21. In the second position, we've got 5, so that would just be 5 1s. And here, since we don't have the change off between 10s and 1s that normally distinguishes different bases, I would leave a significant gap, grouping these together. So we've got 5 1s. Then we've got, 5 in the base 60. And then we've got 4 here. Again, leave a significant gap. Okay. And another way that you would want to be comfortable with seeing this is if we wanted to indicate that this was base 1, this was base 60, and this is base 3600, we might see that as well, just to visually give us the cue that this is the first base, this is the base 60, and this is the base for 3600. But either of these would be acceptable answers. I recommend you pause the video now and attempt this next problem on your own. Write 43,233 in Babylonian numerals. Unpause when you get your answer to check your work. Now, just as my guide, I've written out the fact that the first base to the right is base 1, the second grouping is base 60, the third is base 3,600 for Babylonian symbols. I would look at the number in question, 43,233, and ask myself what's the largest base that could divide it, and definitely we'd be looking first at base 3600. Off to the side we say how many times would 3,600 divide our number, and we get about 12.009. Again, remember all we care about is that 12 divides a 3600 or multiplies there perfectly into there, so we would see what is 3600. If we include 12 of those, how close does that get us to our number? We multiply these, and we see that we would get to 43,200. Now we want to be at 43,233, so we'd see how much is left over. So you take the number that you've got at the beginning, you subtract how close you've gotten to it from your previous base, so we've gotten this close. Subtracting these, checking in our calculator, we see that only 33 is remaining. Now normally you go to the next base over and see how many times that base can go into the number that we've got left over, but if we look at it, we need to fill 33 remaining digits, but base 60 is greater than 33, so that means there's actually going to be 0 base 60s, and we're going to go directly to the base 1. How many in base 1? Exactly 33. Now the Babylonians don't have a symbol for 0, so in this case, we would show it with just an extra space. So we would write 33 in our first position, so that would be 3 10s and 3 1s. So 33 for the first base. I recommend here, since it's ambiguous, if you just leave a space, whether that's a space between base 1 and base 60, or that you're skipping base 60 altogether, draw the second bracket and just leave it empty to show that there's nothing in the base 60 position. And then there is 12 in the 3600 position. How can we check our work? We would take 12 times 3600 plus 0 times 60 plus 33 times 1 and verify in our calculator, does that equal the original value? And it does. Okay. So this would be our answer, and in this case the brackets are helpful to show us that there is nothing in the base 60 position. Next, we're going to look at Mayan numerals. Now, Mayan numerals used what we might call as a modified base 20. Their numbers were written from smallest base up to highest base. So it was written vertically, where the first base is base 1. The next vertical grouping of numbers represented base 20. So that's 20 to the 0 is 1, 20 to the first is 20. Next, we would expect 20 squared, which would be 400, but the Mayans actually use base 360 as the next digit. So that's why we call it a modified base 20. We have these symbols to work with. So the Mayan system had a 0 represented here. 1 is a dot. 5 is a horizontal line. Let's look at some of the features of the Mayan system. So whenever we're looking at Mayan numerals, we would look at the bottom set of numbers first, and then as we increase through group rings, we know we're going to higher bases. At the base, we always start at base 1, next is base 20, next is base 360. So whenever we're converting these numerals, it's similar as before. For the Mayan numerals, you would always write the 5 digits below and the 1 digits above. So notice we've got a 5, a 10, and 11. So we've got our 1s dot here. But then do we see the next digit is not more 1s, but again a line? That kind of indicates as before that this is its own grouping. So this is our base 1 grouping. Next we've got our base 20 grouping. And then finally the remaining dots here, since it's got this vertical separation, we would assume that this is our base for 360. So for the first base, we have got 5, 10, 11. So that would be 11 times 1, plus our next base would give us 5, 6, 7, 8, 9. 9 times base 20, plus our final base is 2. Based on its third position, the highest, we would see that it's times 360. Adding these carefully in our calculator, and we would get 911 as our answer here. Take a moment to look at our next example, B. I recommend you pause the video and attempt this problem on your own. Unpause to check your work. Now as we're looking at this example, we know the Mayan numbers start from the lowest vertically and then increase upward through the different bases. We see we've got the symbol for 5, 10, 15, 16, 17, 18, 19 here. So this grouping would be base 1, and we have 19. The next vertical grouping is the 0 symbol, so that represents there is 0 elements representing the base 20. Our final grouping here would be 5, 10, 11, representing base 360. And if we wanted, we could write it like this. We know that base 1 we've got 5, 10, 15, 16, 17, 18, 19. 19 times base 1 plus 0 times base 20 plus 5, 10, 11. 11 times base 360. Adding all these together, we would get our final answer to be 3,979. So we just saw how to go from Mayan numerals to our number system. Let's now reverse that process. We are going to express our numbers, which we know as the representation of Hindu Arabic form. So 277 into Mayan symbols. I think what might help us is just writing down, we know that we've got the first section is base 1. Next, vertically, we have to write the representation for base 20. And then we've got to write our representation for base 360. And while there are higher bases in the Mayan system, we're not going to see any higher than these. So at most, we would need to show 3 bases, perhaps less. As before, whenever you're working with a system that has a base, you look at the number given and you ask yourself, what's the largest base in this system that could divide into that number? So for instance, 1 divides 277. 20 would be divisible into 277, but 360, since it's larger than 277, would not be divisible, so we don't have a base representing 360. The highest base is 20. We're going to see exactly how many times would 20 divide evenly into 277. In our calculator, we take 277 divided by 20, and it divides exactly 13.85 times. Again, we don't really care about the decimal here. We want to know that it divides evenly 13 times. Exactly how many would 13 times 20, how close would that get us to the 277? You would then off to the side say 20 times 13. and that would be 260. So if we've got 13, which we're going to represent later in Mayan symbols for the base 20, how close that would get us to the answer we're trying to find? Well, we would subtract these to see what remains, and we're only 17 away. Now we've taken care of the base 20. Next we go down and we look, okay, the remaining base is base 1. With base 1, how many units do we need to take up? 17. So we would have 17 for base 1. We've seen how this is distributed across the different base systems. Now we just need to express it in the correct Mayan format. So I would have 17, which could be represented as like 5, 10, 15. So 3 lines would get us to 15. But to write 17, we then need to add 2 ones. So this is 17. Give a bit of vertical space. And then next we're going to write 13, which would be 5, 10, and then 3 dots would get us to 13. Another way that you might see this expressed, just to ensure for clarity, is you could see something like this trying to show that this is the base 1 and this is base 20. Both would be acceptable answers. And as before, we can check our work. We could see what is 13 times 20 plus 17. And if we've got the correct answer, this should give us 277. Checking in our calculator, we get this does represent 277, so we know that we got the correct answer. For the next example, we're asked to translate our number 83 into Mayan symbols. I would begin always by just writing out the base for the Mayan symbols, so base 1, next base 20, next base 360, and then to ask ourselves, we would say what of these bases could be divided into the number given, 83. 360 is too large, but 20 would divide 83. So it would take 20, divide that by 83, and that would be 4.15. Again, the decimal doesn't matter. It just matters that 20 goes into 83 4 times evenly. That will give us 80. So we know we're going to represent 4 in the Mayan symbols later for the base 20 position. Now we wanted to represent the number 83, and so far we've represented 80 of that 83. That leaves 3 remaining to account for the base 1 position. So then we would just write this in the Mayan symbols. So base 1 has 3, 1, 2, 3. Give a somewhat vertical space here, and then base 20 is 4, and that represents 83. Next, we'd want to translate 1,238 into Mayan numerals. I recommend you pause the video and work through this example. When you've got your answer, unpause to check your work. Now in this example, the largest base that would divide 1,238 is 360. So we would first say with our calculator, 1,238 divided by 360 would give us about 3.438 repeating. The decimals don't matter, but we do care that 3 is going to go in the base 360 position. Now if we have 3 360s, we want to see how close does that get us to 1,238. Multiplying these with our calculator, and we would get that brings us to 1,080. Now how much remaining do we have to account for in the following bases? You would take the number that you're trying to express, subtract how much you've already accounted from it, there is a lot of calculator work in these problems, so I would encourage everybody to go slowly, make sure they're not making any typing mistakes, and we would want to account for 158 remaining in our next bases. So we would say, does 20 divide this? Yes. Let's figure out exactly how much. So you just decrease down through the bases to fill in the remaining positions. So we would have 158 divided by 20. So that would be 7.9. Again, all we care about is that it divides evenly 7 times. 20 times 7 would be 140. Now we wanted to account for 158, And through base 20, we got as close as 140. Subtracting those, that says we still have 18 left to account for in base 1. So base 1 would be 18. Now all that's left to do is represent each of these digits in Mayan symbols and show the appropriate bases by the vertical spacing. First, 18 would be 5, 10, 15, 16, 17, 18. Then we would leave significant space, and then we would have 7 in the second position, so 5, 6, 7. Leave vertical space, 3 in the third position, 1, 2, 3. And that would be 1,238 in Mayan symbols. If you want to check your work, you could always say 3 times 360 plus 7 times 20 plus 18 times 1, and then verify that that would give us 1,238 in our calculator. For this next problem, I recommend you pause. Again, work through the problem, unpause to check your work. So we know that we're translating this to Mayan numerals, so I would start by listing out the bases for the Mayan numerals. I know the Mayan system is listed vertically, so base 1, base 20, base 360. And then you would ask yourself, what's the largest base that would divide into this number? Now, since 360 is greater than 344, that would not divide, but base 20 would. In our calculators, we take 344, divide that by 20. That would give us 17.2. Again, all we care about is that it divides evenly exactly 17 times for the base 20 position. We need to see how close has this gotten us to 344. So we would take 17 times 20, and we would say that's 340. Now we wanted to express 344. So far we've been able to express 340, which leaves us with 4 remaining to go in base 1. 1, 2, 3, 4, leave a vertical space, and then 17, 5, 10, 15, 16, 17. And that would be our answer. If we want to check our work, we could take 17 times 20 plus 4 times 1, and we would get 344, so we know that we've expressed our answer correctly. Now, our last historical number system for this section of notes is Greek numerals. In this, we're going to look on how to translate Greek numerals to our numbers, and then also our numbers to Greek numerals. And let's first look at some special features of the Greek system. We see that the Greek symbols have digits for 1 through 9, 10 through 90, and then 100 through 900. Now, special features of the Greek system is that we saw that the symbols top off at 900. So if we want to express a digit higher than 1,000, we could represent multiples of 1,000 up to 9,000 with a small stroke to the left of the unit symbol. So the Greek symbol for 9 is this, which is called theta. So if we wanted to express the number 9,000, 9,000 is equal to 9 times 1,000. So to indicate that we're multiplying by 1,000 times 9, we would write the symbol for 9 and then a small stroke to the left. So this is how we could quickly represent the digit 9,000. If you want to represent something 10,000 or greater, then multiples of 10,000 are indicated by the letter M. And what you would do is you would include the unit symbol, units meaning digits 1 through 9, above the M. So in the Greek system, 5 is represented by the symbol that looks like this. So if we wanted to represent 50,000, 50,000 is the same thing as 5 times 10,000. It's a multiple of 10,000. So we would represent that in the Greek system by having the M symbol, which means multiply by 10,000. What are we multiplying by 10,000? 5. So with this, we can very quickly represent very large numbers through this system. Now, the Greek symbol doesn't have a base system. What's happening is you always write the largest digits at the farthest left, and then as you read to the right, you're going to be looking at smaller digits, much like our numbers. So let's work through our first example here. We are asked to represent this in our number forms. Let's first just identify where we might find these symbols in our table above. So 30 is represented by this symbol, and then 1 is represented by this symbol. We know in the Greek system it's larger number and then smaller number to the right of it, so this would represent 31. So this is the idea of 30 plus 1. Let's look at our next example. Now in this case, we found the symbols in the table above. This represents 300 plus 20 plus 5, which would be the number 325. I recommend you pause the problem or pause the video and then find how we would represent the next example here. Unpause to check your work. Identifying the symbols, we would see that this represents 600 plus 4, which would be the number 604. Now, whenever we go from our system to Greek symbols, it might be helpful to break down the different positional system that our numbers are representing. We see that we've got 4 in the tens place, so that's 4 times 10 plus 8 is in the ones place, 8 times 1. Or we could write this as 40 plus 8. So we've kind of broke it down to the units and the tens. Let's look for the symbol for 40 in our table. So we see 40 is represented by this symbol. So I would write that first. Always the largest number first to the left, and then as you move to the right, going through smaller numbers. Okay. And then we would look for the number that represents 8. We see that here. So this would be the number representing 48 in the Greek system. Now for the next digit, 3000, we look at our symbols and we see that the largest is 900. So then we have to remember the special feature of the Greek system. If we're multiplying by 1000, we show that with a dash to the left. 3000 is the same as 3 times 1000. So we ask ourselves, what are we multiplying by 1000 to get 3000? 3. So we would look for the symbol for 3. And if we just leave it like this is 3. To represent 3000, we put a little stroke or dash to the left of it, and this represents the number 3000. For our next example, we see it's 40,000. That's a multiple of 10,000. Specifically, it is 4 times 10,000. In the Greek system, multiples of 10,000 have the digit that it's multiplying by 10,000. In our case, that would be this digit for 4 above the m. Okay. So we would draw our m relatively larger, and then we would draw the symbol for 4 above it. So this represents 4 times 10,000, which would be 40,000. I recommend you take a minute to pause this video and express this in Greek numerals, looking at our table here. Unpause to check your work. Since the Greek system has representations for digits, multiples of tens, multiples of hundreds, and then we know how to represent multiples of thousands and 10,000s as well, I would begin the problem by breaking down 7,900 or 7,694 could be written as 7,000 plus 600 plus 90 plus 4. So in this case, I've broken it down into, okay, what are the single digits, the multiples of 10, multiples of 100, multiples of 1,000. Now 7,000 is the same as 7 times 1,000. In the Greek system, whenever you're multiplying by 1,000, what we need to do is we need to find the digit that represents what we're multiplying by, and then put a dash to the left of it. So we would try to our best of our ability to draw this symbol. Okay, and that's 7 left alone, but when I draw the dash next to it, that represents 7,000. So we always go from largest and then moving to the right to smallest. So we've represented the 7,000. Next, to represent 600, there's actually a whole symbol for 600. So we would write that next. Then to represent 90, we look at the symbol chart. We've got a symbol for 90. Finally, we would write the symbol for 4, which we found here to be, okay. So this would represent 7,694. So that's it for this video. As you're working through your homework problems from this section, I recommend you go to Canvas and find the file that says Chapter 4 Formula Sheet, and you'll be able to find all of these symbols in a single picture format. And if you have a printer, that might be a useful thing to print off. But if you don't, then I recommend just taking a bit of time and writing that out on notebook paper so you don't have to flip back and forth to see all the different symbols from our different historical number systems. Thank you.